So in the last class up to this point we discussed, right? Here it is simply focal point. What we said, focus or focal point. So here what is actually focal point or focus means, here parallel beam of light rays and they are parallel to the principal axis incident on a convex lens. They refracted through the lens. After the refraction they are going to meet at a common point. So that common point is called as focus or a focal point. So that definition is given here. If parallel beam of light rays incident on a double convex lens, they can converge at a point after refraction. So this converging point of light rays is called as focus. That is only denoted here f1. Then I said to measure the distance or the length between P and f1. Distance from the pole to the focus. That is called here focal length. That is called here focal length. Here that definition I am showing here. Look at the distance between the optic center and focus is called focal length. Here the same explanation we are able to give by using the symbol of a convex lens also. Look at here. I am taking now symbol of the lens, double convex lens symbol that we are using here, double headed arrow. That is your symbol of a convex lens. So using this also you are able to explain that here center of curvatures C1 and C2 of the double convex lens. Then it is the principal axis. Identify the pole, then incident the parallel beam of light rays. What happens after the incidence? Refracts. Then after refraction they are going to converge at a common point. That point we are given as here focus, right? So that is named as f1 because it is first surface, right? So if you incident the light rays from the second surface, that point will be observed at the left side. So that point we are taking as f2 here. So two focal points available with a double convex lens, also double concave lens. So these points are called as here focal points, and the length between the optic center to the focus is called focal length, denoted by letter small f, right? So this is about this question answer. What happens if parallel beam of light rays incident on a double convex lens? The same question I am asking you to answer. What happens if parallel beam of light rays incident on a concave lens? So now the lens is changed. Automatically what happens? Behavior of light rays also changes after the refraction. So let us look at that. Here I am drawing the lens called as double concave lens. So here first surface center falls left side. So as I given a dot here. So that is C1 here. Then second surface center towards right side, that is given as C2 here. Then join them with a line called as principal axis. Then identify the pole just in the middle of the lens. So that is called optic center of the lens. Then what to do? Here incident the parallel beam of light ray, that which is parallel to the principal axis. I am stressing this one. Carefully listen. Parallel beam of light rays and it is parallel to the principal axis, right? So what happens? Here light rays incident on a double concave lens. So here to understand about that one, simply we will use the previous 9th class knowledge to know about the behavior of light rays after the actually that refraction is taking place from the second surface. Look at here, small mistake I did. That ray already in the denser medium, right? Here it is entered. So it is in the lens. Then what happened? It is coming out into the air at this point here. So we have to construct the normal from the right side because from the right surface it is refracting, right? So I am constructing the normal from C2 towards the point of incidence, right? Here imagine that angle here, where at this point I am showing you here. Look at. So what is the angle here? Somewhat. We don't know the value, something x. Then it enters into the rarer medium. That angle you will take greater than x or less than x in the rarer medium. It is greater than x. In this condition only we will say it is bending away from the normal. See here, that light ray is below the principal axis, another side it is above the principal axis. So in which direction it moves? Upward or downward? Upward. So it is called as bending away from the normal here. Look at. So here I told you that the light ray which incident normally remains undeviate. So that red color ray I shown special, right? Because it is incident normally along with the principal axis. It remains undeviate after refraction. So that is given with the blue color after refraction. Now look at here what happens to this rays above and below to the principal axis after refraction. Look at how they are to the normal, moving away from the normal or towards the normal. Just you have one normal there. How they are? Away from the normal. So here what happened after that parallel beam of light ray incident on a concave lens, double concave lens or biconcave lens. What happened here?
Diverges.
They are going to meet each other at a point.
Diverges.
Each other? No. So that we can call it as diverging of light rays. So you may know this lens is known as called another name based on the behavior of light rays after refraction.
Diverging lenses.
Very good. It is called as diverging lens due to this behavior only. Okay. Here, what to do in this case? How to find out the focal length? Right? Simple technique we will follow. Here, diverging point, where we can locate the diverging point. Right? So, locate the diverging point by tracing the path of light ray in the backward direction. Right? So, it is moving in this direction. Its backward direction is downward. So let us construct the backward rays. See here, blue color line, dotted lines showing. Always draw the backward ray with dotted line. Then for the second ray, for third ray, next along with the principal axis, it remains along with the principal axis, no need to show, or you can draw it, no problem. See, how do they look like? Diverging from a point. All the light rays diverging from a point that which lie on the principal axis. Is it clear? So that point identifying as here
Focus.
So it's number 1, F1, because it is first surface. Light rays incident on the first surface. So that surface focus here identified. So from this point all the refracted light rays appear to be emanate. Right? So this point is called here focal point. Okay. What about right side? If you change the incident light ray direction opposite, what happens? That focus also changes towards that side. So that is named as F2 here. Next, look at here what happened. What the generalization we are giving. If parallel beam of light rays incident on a double concave lens, they seem to emanate from a point on the principal axis after refraction. Do you understand this sentence? Is it clear now? They appear to diverge from the focus. We can find out the focus in case of concave lens by drawing the backward rays. Then here that point is called as, the diverging point is called as focus. The distance between the optic center to the diverging point is called as focal length. So like this we can find out. We can show this representation by using the symbol of a double concave lens. So here it is the symbol of double concave lens. See the symbol of here it is written as a double convex only. Here it is the mistake. Notice this one. It is concave. Right? So it is concave lens symbol. Then identify its center of curvatures. Join that. This is called as principal axis. Then locate the pole or optic center. Next, focal points. How we are identifying that focal points? Using the parallel beam of light rays that is parallel to the principal axis. Then that behavior we already know. They appear to diverge from a point. That is, we are giving us here its focus F1. then it is called as focal point. Right side also we will do the same thing. Then keep these points in your mind. What is behavior of light rays after refraction, then how they are appeared, diverging or converging, then what that point is called as, after that the length between the optic center to the focus. Okay, so this is the information we have to know. Now our discussion is about this one. What is behavior of certain light rays when they are incident on a lens, whatever it may be the lens here, not important, but that certain light rays, simply we are selecting the rays to incident either along with the principal axis or passing through the pole, right? Then next normal instance, like that we can select, and parallel. So how they are behaves after refraction in case of a convex lens and in case of a concave lens, both we will discuss, right? So once look at that one. So for that I am naming here for the situation 1 as situation here. So what is that situation? Here it is ray passing along the principal axis. It may be any lens. It may be double concave lens or double convex lens and the other lenses also. But in 10th class we are discussing only 2 types of lenses. One is double convex lens and the other is double concave lens. Then first I will choose here. Can you please name this? Double convex lens. Then identify the pole, center of curvatures, C1 and C2. Particularly identify them. Join the center of curvatures. This is called optic center or principal axis. Next, find the focal lengths on the principal axis where they will be. Right. So identify them as F1 and F2 here. So this is the first one. Then come to your situation. What is that? Ray passing along the principal axis. So here look at blue colored ray. It is along the principal axis. How it behaves after refraction? Are we able to generalize its behavior after the refraction? Yes. So here actually this is considered to be normal instance, right? So this is simply continues in its path without any deviation, remains undeviate. What we can say? Remains undeviate. If any ray passing along the principal axis of a double convex lens, it remains undeviate after the refraction. What happens if we incident that ray passing along the principal axis on a double concave lens? So let us take the symbol of double concave lens here. Identify the pole. Next name it. After that identify the center of curvatures as you see here, C1 and C2. Then join them, called as a principal axis. After that identify the focal points here, F1 and F2. Then choose that ray that passing along the principal axis. See here, blue colored ray passing along the principal axis, right? Then one more also you are able to say here, same thing, using the same ray passing through the optic center of the lens. See the both figures, it is passing through the optic center of the lens also, right? What happens? It is also remains undeviate because it is also normal instance. Is it clear? So this is given in your textbook figure number 9b. Observe the both figures. What you can give the generalization here? What the generalization? Ray passing along the principal axis of any lens
Remains undeviate.
remains undeviate. This is the generalization. See, situation 1, ray passing along the principal axis of any lens and remains undeviate. So this is the generalization. Is it clear? Situation number 2. So what is that situation I am selecting here? That simply behavior of light ray before refraction here. How it is? It is passing through the optic center of the lens, right? It may be concave lens or the convex lens. So first I will choose the convex lens. So complete the process as we discussed in the previous case, right? I got all the points. Double convex lens, principal axis, center of curvatures, focal points. Then choose a ray that what you are created the situation here. What the situation is? Ray passing through the optic center of the lens. So I am selecting the ray to pass through the principal axis as I shown you here, right? It may be you can take it below from the principal axis also, not a problem, right? I am following like this. Okay, what happens after refraction? It remains undeviate, no deviation, right? The next, it is by the double concave lens. So complete the all process. So I got its respective f1 and f2, c1 and c2. Then instant light ray, as you discussed in the figure number 10 here. Look at that one. Ray instant on the lens exactly to pass through the focus. So in this case also the ray remains undeviate. So remember this situation 2 here. It is given in your figure number 10b. So what you can give the generalization from the both 10a and 10b? Ray passing through optic center of any lens remains
Undeviate.
undeviate. So it is also undeviate. Is it clear? The next situation. Situation number 3 it is. So what the situation is created? Rays traveling parallel to the principal axis. Is anybody give generalization for this one before explanation? Okay, I will show you. After that you try to give explanation. So I will complete the process. What double convex lens, center of curvatures, then next principal axis, after that identifying the pole, then respective focal points f1 and f2. Then instant the parallel beam of light ray, that is parallel to the principal axis. Rays traveling parallel to the principal axis. Is it clear now?
Yes, sir.
So what you can give the generalization here?
All the rays converge at a point
Where?
on the
Focus.
F1.
On the principal axis, especially at
F1.
f1. Very good. So that is we are giving the generalization. So here all the light rays are going to converge at a common point. This is the behavior of light rays, right? So this is given in your textbook figure number 8a. Then next, what happens if you instant that a parallel beam of light rays which are parallel to the principal axis on the double concave lens? What do you give generalization here?
Light rays will diverge.
Diverge. So simply diverging means it is not enough. How they look like? They seem to be emanate from the focus. See here. Is it clear? Backward rays, they converge at a common point. So that is diverging point of light rays. Is it clear?
Yes, sir.
So here it is the behavior of light rays. What you can give the generalization here? The generalization is converge at the focus or appear to diverge from the focus. Depending on your lens, you can choose that generalization. Okay, na? Is it okay now?
Okay, sir.
Right. So we'll go for the situation number 4 here. Are you following your textbook or not?
Yes.
Let's look at that. Okay, situation 4. Can anybody say the situation 4 what it is?
Ray passing through focus.
Very good. Ray passing through the focus. What happens? So many rays I can consider here. Look at them. What happens after refraction? Is there any hint to you in the diagram? That means what the situations we have discussed previously. Is it work out? 1, 2, 3 situations. Can I use any situation? See, blue color light ray. I am giving hint. Blue color light ray. It is along the principal axis and also through the focus. So what happens after refraction? Will it remains in the same path or changes? Remains undeviate, right? So this is, see, I shown that with the green color here. How they are becoming parallel to the principal axis. It is becoming parallel to the principal axis after refraction. So here consider that is in case of double concave lens. So let me complete this process. Look at here. I will get the parallel beam of light rays to instant, diverging of light rays. That means here you are unable to say ray passing through the focus. In case of double concave lens, we can say that ray appear to meet the focus, but they cannot meet. Appears to meet the focus, right? So what happens in this case? Blue color ray remains in its own
Deviated.
undeviate. Okay, so what happens to the remaining? They becomes parallel. So here we will use this backward light rays. They appear to meet at f2, but we cannot see them to meet there. Here they diverge because the nature of double concave lens is diverging. So look at that green color light ray, undeviate, because that blue color light ray incident on the double concave lens along with the principal axis, or it appears to passing through the focus. This is the situation given in 4.11 B it is. Is it clear? All the 4 situations. Is it clear? Any doubt in them?
Yes, sir. Clear.
We have to remember these. Practically observe and remember them. Then I will discuss a special situation with you. Right? What it is? Here I stressed at one point in the previous discussions. What that? When I use parallel beam of light rays, I said to concentrate there. Parallel beam of light ray, and it is parallel to the principal axis. Right? Now I will consider a situation that parallel beam of light rays falls. That means incident on a concave lens or a convex lens, but they are not parallel to the principal axis. They are making something angle with the principal axis. See here. Is it clear now? What the special situation is? Look at here. I will show that diagrammatically. So principal axis completed. Now the light rays are incident. How that light rays are each other? They are parallel to each other. Then are they parallel to the principal axis or making something angle? Making angle with the principal axis. It is look like a transversal line. See, blue color one. All the angles are same or not? So they are making angle with the principal axis. In this condition, what happens? What the situation you are observing? How to find out a focal length? Can you find out focal length in this situation? By incident parallel beam of light ray on the double concave or double convex lens, but they are not parallel to the principal axis. Is it possible? Is possible or not? So nothing to say. You are decided. Okay, tell me the behavior of that blue color light ray, which is looking like a passing through the optic center of lens.
Remains undeviated.
Very good. It remains undeviate. So I completed that process. It remained undeviate. What about the remaining? What is the behavior of a lens here towards parallel beam of light ray? Converging or diverging?
Converging.
Converging. So where they can converge? On the principal axis. But where is the principal axis here? Not there. So you can imagine that a blue color light ray path only is principal axis. Right? Okay, we imagine, sir. But where the remaining light rays are going to converge? That is the question here. So for that, just we are doing one thing. Drawing a perpendicular line from the focus of the lens to meet this light ray. Is it clear? Where they can converge or they can meet, coincides, which that line, dotted line, what I drawn perpendicular to the principal axis and passing through the focus. Right? So there you have to keep one point. So look at encircle that with the red color. So that point is important to you. Right? So identify this point first. Then look at here. What the line I am calling here. That line what I have drawn is called as focal plane. What is focal plane here? Simply what the line you are drawing which is perpendicular to the principal axis and it meets this undeviated light ray after the refraction. So that point important for us. So the dotted line is called focal plane. Focal plane is the plane perpendicular to the principal axis at the focus. Right? One definition got on the screen. Right now, just it is identified as a focus for that we can call it as imaginary focus. What it is called as imaginary focus. that light rays all together converge at a point which you identified on the focal plane. Simply by rotating that light rays, you are able to get this converging point exactly at focus. If you are able to imagine that, rotating the parallel beam of light rays, then the focal point which you got below the principal axis moves onto the original focus along the focal plane, right? So this is happens. This is called a special situation, right? It is given in the figure number 12a in your textbooks. Look at what happens if that parallel beam of light ray which makes angle with the principal axis and incident on a double concave lens. So I completed that drawing of double concave lens here, identified all the points. Then look at that light rays already incident on the concave lens by making angle here. Look at that angle also I shown. Okay, a ray passing through the optic center, right? That ray remains undeviated, that we know. Then tell me the behavior of a concave lens towards parallel beam of light rays. Is it diverging or converging?
Diverging.
So all the light rays move away from the principal axis. How to identify that one? In the previous case, just we drawn backward rays onto the focus, but there is no focus. So I have to identify the focus with the help of focal plane here. See, through F1 I drawn focal plane. Is it clear? Then that ray which is passing through the optic center coincides with the focal plane. That point you have to identify as its imaginary focus, as F0 or something. You can give the name also, no problem. Then from that point, these all the light rays are appear to be diverged. See, reversely I am coming. From the focus to the point of incidence, I got a rays, dotted lines, right? Then what happens after refraction to these light rays? They can move along these dotted lines I shown. Look at them in that direction. So how these green color light rays are appears? They are emanating from the imaginary focus that which we got on the focal plane. Is it clear now? If there is any confusion, I will clarify that one. Sir, it is something confusion. Converging, diverging point always lie on the focal plane, sir. If I take from the below principal axis or with a different angle, do you have any doubt like this? Let me show you that. Right, so first look at that figure number 12 and 12b in your textbook. See here, the rays converge at a point or appear to diverge from a point lying on the focal plane. So that is the generalization we are giving when a parallel beam of light rays incident on a double concave or double convex lens with some angle, that rays converge at a point or appear to diverge from a point which lying on the focal plane. So this is the generalization for this special situation. Now look at here. Are you able to see here what is happening? Just focus on the concave lens first. Anybody please comment about that first figure? Concave lens, sorry, convex lens, first one, convex lens. What happening? That rotation given, yes or no? Rotation given. So here, while they are rotating up and down, that means above the principal axis, below the principal axis, is there any change in the diverging point or a converging point of light rays? So this is what diverging point. This is what converging point. So here look at that converging point moving along the principal axis or focal plane or changing. Here diverging point. This diverging point exactly on the focal plane or is it changing? That you have to concentrate. So once again I will show you that movement by the light rays. See here, they are moving. What happening here? That converging point and diverging point changing its position above or below, that exactly on the focal plane. Is it clear or not?
Yes, sir.
Right. So this you have to concentrate. Okay, na? Shall I move to the next one? We have to learn the rules to draw the ray diagrams. Okay, at least we will complete the rules. So now topic is rules to draw ray diagrams for image formation by the lenses. Sir, these lenses can form the image. Do you see any image formed by a lens? In 6th class, light to shadows and images, in that we have shown the image on the paper using a magnifying lens. Do you remember that? Through window. Standing a person or something outside object we used to focus on the paper. Maybe you forgot. Do it. You will get the image. So how that image is explained, right? So we can use ray theory to explain the formation of image, right? So for that, here simply what it is, principal axis, right? How I am moving, that you have to keep it in your mind, right? Then choose a point on the principal axis to draw the suitable lens here. So first I selected double convex lens, right? Then that principal axis and lens coincides each other. That point we are taking as here principal axis and identified with the letter P. Then identify its center of curvatures and focal points respectively. Name them. So I got. Then what to do? Just you have to select object where you are placing them. So always the object is placed on the principal axis. Keep it in your mind. Okay, always the object is placed on the principal axis, right? So that object now I have shown with the upward arrow. Always we are showing the object in ray diagrams with upward arrow. Don't take the downward, only upward. Compulsory, it is conditional. So upward arrow drawn. Then second point. First point is always place the object above the principal axis, that is shown by the upward arrow here. Then next, choose a point where it is at the top of the object. Where we have to choose a point. See here, that red color point I selected at the top of the arrow, right? It is maybe small to you. Just try to identify. I will encircle that one point here. There is the point. Here it is, right? So look at that point. From that point, choose two rays. Which two rays? According to the situations 1, 2, 3, 4, which are possible. What are the 4 rays? One is parallel to the principal axis, one is passing through the optic center, one is along the principal axis, and the other is passing through the focal point. Okay, so they are the 4 situations. Any 2 you have to choose which are possible to you. So always we are selecting only 2 rays. What they are here? One is parallel to the principal axis. This is fixed. That choosing of light rays are fixed. One is parallel to the principal axis and the other is passing through the optic center of the lens. This is. See, I shown that where I chosen that point above the object, top of the object. From there only chosen 2 rays. One is parallel to the principal axis and the other is passing through the optic center of the lens. Then already we have given generalization for the ray which passing through the optic center of lens. What is that generalization in any lens? Remains undeviate. So first you have to complete that one. It remains undeviate. So goes in a straight direction. Then ray which is parallel to the principal axis, incident on a double convex lens. It can be converged or diverged.
Converged.
Converged. Where?
At F1 on principal axis.
Right. At F1 on the principal axis. Then look at, do you got any converging point of refracted light rays? I may got. After refraction, the 2 rays are going to meet each other or not? How they are appearing? If you extend it, it can meet that. Okay, extending. So they are converging at a point. Yes, that green color point I have shown here at the arrow, right? So my cursor is placed at a green color point. Look at that. So this is the point what you selected for the object. What it is? Image point, right? So here is the image formed what the point you have chosen on the object. Then what about the remaining? Right? So to find out that one, just you have to draw a perpendicular line from this point onto the principal axis as you see here. Right? So from the principal axis, you have to give the direction towards the point. So this is the direction of image, facing direction of image. So object is faced above the principal axis, image faced below the principal axis. How they are standing? Opposite facing each other. They are facing opposite to each other. So this type of image is called inverted image. Right? Okay. Then identify a point where that perpendicular meets the principal axis. There the bottom of the object will be formed. Okay. What happens in case of concave lens? The rules are same or different? Are the same or different? So same, right? Only the lens will change. Okay. One more you have to remember. The behavior of a concave lens is diverging. So it cannot meet the focus. So we'll go to the next one. Logical rules. What I am giving to remember them, right? So first of all, you have to take your paper horizontally and put your scale as you see here. Long scale. Use long scale. Then start from there. What I am showing with the pencil. Look at carefully. So draw a line and name it as principal axis. Is it clear? Then remove them. What to do? Select a point middle on the principal axis to draw your lens. Right? So I am drawing the lens now. What type of lens? Double convex lens. Then remove your scale. Identify the pole here. Pole identified. Next, identify center of curvatures as you see here. So I am following using the rule here that what r equal to 2f, double to the focus. Right? So exactly that focus lie between the pole and the center of curvature. So for that I am using a logic 8 centimeters here. You can take depending on the paper length, 10 centimeters available means you can take 5. So here see, at 4 centimeters and at 0, I am identifying the points here. Look at that pencil. So I took one point there. Then next, one more point at 0. Look at that. I got 2 points now. Right? So remove your scale and move to the opposite side of the lens now. Follow the same logic. 0 to 4 centimeters, 1 point. Next, 4 to 8 centimeters, another point here. Is it clear now? Up to here?
Yes, sir.
Yeah. Following carefully. So removing the scale. Then respectively you have to give them as C1, C2, F1, F2. Is it clear? Then I choose again scale here. How I placed it? Above the principal axis. Let me select the object height exactly width of the scale. What is the object height selected? Width of the scale. See that arrow drawn exactly equal to the width of the scale. Then select the top of the object selected, that red color pointer. Next, choose the ray parallel to the principal axis by keeping your scale as T is. Draw it first. Why I am given this logic? To draw parallel line easily. Otherwise you cannot draw the parallel line. You will get confusion. Object height taking other than width of the scale. Right? So follow this logic carefully. Width of the scale only you have to choose. Then second ray already put your scale like this. Then draw the ray to meet the optic center. We know the behavior of this light ray. It passes, remains, undeviates. So again complete that behavior of light rays. Is it clear how to draw them?
Yes, sir.
Then I got the point, converging point. So let me select that one. Now see, drawing the perpendicular onto the principal axis like this. Then it is the rules.